So, before going into the synthesis of these nanocomposites, I would like to briefly introduce the background of my work, why we are planning to synthesize this nanocomposite, because we know plastic materials actually they brought considerable convenience to our daily lives because they are low cost, they are lightweight, and they offer high durability and excellent chemical stability. So, but if you see from the perspective of environment, they consider them as persistent pollutants because they endure within the ecosystem for extended time periods. So, the plastic plastic items like after their use, if you throw into the environment, they degrade into minute particles which we know as microplastics, which are like less than 5 millimeters in size. So, the degradation of microplastics is a very a very big problem nowadays, because the big plastic items you can recycle, but the microplastics you cannot recycle them, and only the way you have to degrade them. So, nowadays people are using techniques like biodegradation, photodegradation, and pyrolysis for the degradation of microplastics. So, in this line we have a thought of using photodegradation for the degradation of plastic. So, actually the photocatalysis, why it is important, because the photocatalysis is a very promising tool for plastic pollution, because it only requires a photocatalyst and a light source. And actually because we know, like most of the times we are just dealing with the developing countries and remote locations where we cannot install the complex systems for the degradation of plastics. So, the photocatalysis can offer a sustainable solution to deal with the plastic degradation. So, if you see what are the challenges involved in using photodegradation for the plastic degradation? If you see that mostly the plastic items, they are made up of polymers like polyethylene, polyvinyl chloride, and polystyrene. But if you use the visible light, because they are not like good visible light absorbers, so how we can make them absorb the visible light so that we can degrade them? So, the solution, like we can do it in two ways. The first one, like we can use the visible light for extended time periods. So, and we can increase the intensity of the visible light, but that is not an economically viable solution, but that is not a cost effective solution. So, second one, we can do that, we can impregnate some kind of visible light photocatalyst into the plastic or polymers, and then we can easily degrade the polymers actually. So, that the second one we have taken, and we try to impregnate a visible light photocatalyst into polymer, and we try to see the degradation, how they are responding. So, in this study, that is why we have synthesized a bismuth oxychloride zirconium oxide nanocomposite via co-precipitation method, and we impregnated that catalyst into LDPE film and try to see how it is responding. So actually the key challenges involved in this study, like we have used a bismuth oxychloride zirconium oxide nanocomposite. So, if you take the bismuth oxychloride, it offers a number of advantages. Like the first advantage is it is a layered structure material, and it has internal electric field that supports the charge separation, and it also offers, like you can tune the morphology of this bismuth oxychloride. But the key limitation of using bismuth oxychloride is it has a wide band gap, that is like fall in between 3.2 to 3.5 electron volts, and there is a rapid electron hole recombination you can observe in the case of bismuth oxychloride. So, these two things severely limit the utilization of bismuth oxychloride as a photocatalyst. So, we need to modify the bismuth oxychloride via using some other composite like zirconium oxide, then we can have a efficient visible light photocatalyst. That is why we have used a zirconium oxide, which is an N-type semiconductor, and we prepared a nanocomposite. So, once you have the bismuth oxide zirconium oxide nanocomposite, that suppress the electron hole recombination, and it also improves the charge separation, and it promotes oxygen vacancies. So, that will facilitate the hole attack on the polymer. So, that is the rationale behind this component design. So how we have synthesized this bismuth oxychloride zirconium oxide nanocomposite? This is the process for the preparation of this nanocomposite. So we have used bismuth nitrate pentahydrate as a precursor, and we have used zirconium oxide, zirconium oxychloride as a precursor, as a zirconium precursor, and we have used a co-precipitation method and prepared the bismuth oxychloride zirconium oxide nanocomposite. We have prepared the nanocomposites using different stoichiometric ratios of precursors like 1:1, 1:2, and 2:1. So, and we have also used different calcination temperature for each stoichiometric amount of nanocomposite, like 400 degrees centigrade, 500 degrees centigrade, 600 degrees centigrade. So, I mean, you can see that we have chosen the calcination temperatures based upon the thermogravimetric analysis of bismuth oxychloride, because if you take if you see the thermogravimetric analysis of bismuth oxychloride, it exhibit I mean thermal stability up to 650 degrees centigrade, 650 degrees centigrade. So we have chosen 400, 500, 600 as our calcination temperature for our nanocomposite. So similarly, like I mean after like you can see that bismuth oxychloride actually after 650 degrees centigrade there is a significant loss of 27%, and that is due to the formation of bismuth oxide, and in the bismuth oxychloride zirconium oxide nanocomposite also we find 12% loss actually after like 600 degrees centigrade. That is also due to the bismuth oxide formation. So we have also I mean after preparation of this nanocomposite, we have taken the IR spectra of that nanocomposite, and we have seen the bismuth oxygen stretching at 529 centimeter inverse and bismuth chloride stretching at 1152 centimeter inverse. It confirms the presence of bismuth oxychloride in our composite, and we also observe zirconium oxygen zirconium, that is asymmetric stretching at 761 centimeter inverse, that confirms the presence of zirconium oxide in our nanocomposite. So after that we have taken the XRD pattern of our nanocomposite, because we have calcinated at different temperatures, 400 degrees centigrade, 500 degrees centigrade, 600 centigrade our nanocomposite. Like you can see the from the XRD pattern, like if we increase the calcination temperature, the crystallinity of the material has got increased, and we also see the peaks correspond to the bismuth oxychloride and zirconium oxide in our composite material. So it is a composition of both the materials. So after that we have studied the pore type and pore nature of our prepared nanocomposite using the bed isothems. So from the bed isothems what we find that our prepared nanocomposite like exhibit the type 4, that is IUPAC classification, type 4 curves actually with H1 hysteresis loop you can see. So mainly we have studied the surface area, like how the surface area of our catalyst is improved. So if you see the bismuth oxychloride, the surface area from the bed isotherm is 16.3 meter square per gram. So when you have a composite, a nanocomposite, it's 34.8. So if you have a better surface area, that offers additional reactive sites, that is very good for photocatalytic degradation. And we also done like the additional surface area, what it will do, that will diffuse the photogenerated electrons efficiently, electrons and holes efficiently, so that you have a better photocatalytic activity of the material. Sorry. So after I mean preparation of our nanocomposite, we have taken the UV visible spectra of that, and we have estimated the band gaps of the material. This is the bismuth oxychloride band gap, that is 3.56 electron volts, and the zirconium oxide you have 3.10. So you can see our nanocomposites 1:1 and 2:1 and 1:2. The different stoichiometric quantities we have used. From 1:1 you can see the band gap is 2.15 electron volts, and the 2:1 composite it's 3.10, and 1:2 material it is 2.31. From this you can say that the 1:1, the stoichiometry precursors which we have prepared, that is exhibiting the lowest band gap. So it means it is a good visible light photocatalyst from this UV visible DR spectra. So after preparation of this material, we have taken the SEM analysis of this material also. So bismuth oxychloride, you can see that there is a flower like structure, the floral structure you can see, and this is like at different resolutions. From the literature we know that the zirconium oxide is like shows the elongated rod like structures. When you see the our material, this is our material EF, that is the composite actually, you can see that it contains the distorted floral like structure, and it is also having the elongated rod like zirconium oxide composites in it. So it confirms the presence of both bismuth oxychloride and zirconium oxide in our material, and this is the elemental mapping, and this is the index spectra of our compound, which also further strengthens that we have the both composites in our material. So we have further conducted the XPS analysis of our composite to find out that it contains all bismuth, oxygen, chlorine, zirconium elements or not. You can see that this is a bismuth oxychloride. You have the bismuth 4f orbital and oxygen 1s orbital and chlorine 2p orbital. If you see the composite, you can have the bismuth 4f, oxygen 1s and chlorine 2p, and in addition to it you have the zirconium 3d orbital also in it. So after successfully preparing that nano composite, we have fabricated the LDP impregnated bismuth oxychloride zirconium oxide impregnated LDPE composite films. So we have prepared the polymer stock solution, then we have dispersed our catalyst in different weight percentages. We have used 1 weight percent, 5, 7, 10. And we have used solution casting method and to disperse our catalyst, and we have used thermal drying, and we have finally have the composite films. You can see we have the composite films. So this one is our composite film. So after like having that composite films, we have set up our visible light photodegradation experiment. This is a model experiment, like just it is a representative image. We have used the household fluorescent lamp. So we have used two types of lamps, 50 watts and 90 watt, and we have placed the films in 10 centimeter distance, because and the light intensity varies, like for 50 watt you have 0.039 watt per centimeter square, and 90 watt you have 0.072 watt per centimeter square, because the light intensity varies for 50 watt and 90 watt. So after like irradiation, we have taken the weight loss of the LDPEC composite films actually. We have taken like 10, we have used 1, 3, 5, 1, 5, 7, 10. So for 10% we got the better results, we got the better degradation. So the bismuth oxychloride zirconium oxide calcinated at 600 degrees centigrade given us the highest degradation percentage of, that is 48.67% under 90 watt household light. So we have further confirmed the degradation and the formation of CO groups, carbonyl groups, hydroxy groups, carboxyl groups in the composite using IR spectroscopy. So further strengthen our study, we have also studied the carbonyl index of the LDPE film. So from the carbonyl index, because the 90 watt bulb this is actually, so from the 90 watt bulb we have the approximately 2.0 carbonyl index, more than 2.0. From the 50 watt bulb we have like approximately more than 1.41, in between 1.4 to 1.6. So the 90 watt is giving better results, and actually the zirconium oxide, bismuth oxychloride zirconium oxide, like to assess what kind of heterojunction it is, we have also conducted the Mott-Schottky plots of this nano composite. From this Mott-Schottky plots, we observed that you see the bismuth oxychloride is showing the negative slope, so it is a p-type semiconductor, and the zirconium oxide is going a positive slope, it is a n-type. And if you see the composite bismuth oxychloride zirconium oxide, we have an inverted V shape actually, so that represents a p-n junction formation. So the p-n junction formation just increase the charge separation better, that gives you a better charge separation, and it also gives you the longer lifetime period, longer life periods of your electrons and holes. So we have further strengthened the better photocatalytic efficiency of our bismuth oxychloride zirconium oxide using the photoluminescence spectra. From this you can see that in the case of a composite you have a depressed photoluminescence spectra. It means that this is a better photocatalyst than the composite materials, than the bismuth oxychloride and zirconium oxide. So after the photocatalytic degradation, like after visible light exposure, we have taken the FSM images of our LDPE films. So this is the A is the pure LDPE film. Okay, the second one is the bismuth oxychloride loaded LDPE film. So you can see that. So there is like little bit deformations you can see, and the C and D, these are the bismuth oxychloride zirconium oxide LDPE film under visible light, 50 watt. 50 watt also you can see something, but at the 90 watt LED bulb, when we have used, you can see that there is a major deformations happen. This is due to the liberation of volatile organic compounds like CO2 from this particular LDPE film. You can see the major H is the major degradation, 48.67%, which I have shown. So previously I have shown in the weight loss experiment. This is at H1. So we have further studied the LDPE films actually using the XPS spectra. So this is the XPS scan spectra. So you can see that. So this is the before the visible light exposure. So you can see there is a very small oxygen 1s peak. So after 24 days of visible light exposure, you can see the oxygen peak is increased. It means there is a severe oxidation and decomposition of the LDPE film. You can see from that. So these are the deconvoluted XPS spectra. So you can see various things like various formation of carboxylate groups, carbonyl groups, C hydroxy groups. You can see that because here before exposure, after exposure, there will be a broadening. You can see that. So this is the after exposure of visible light, you can see after and before and after. So before and after, you can see that the elements like the zirconium and bismuth, actually the bismuth you can see before visible light degradation, the peak intensity is very low, but after exposure you can see the peak intensity has increased. So this is due to the better exposure, because like the LDPE film is degraded so that you have the only catalyst, so you have a very high intensity of the peaks you are getting in XPS. So this is the EDX spectra, further confirms the presence of all the elements. So we have also proposed the mechanism actually, like how this system is working for the LDPE degradation. So we have the bismuth oxychloride, we have the zirconium oxide. So after visible light absorption, the electrons from the valency band, they go to the conduction band, and which leave like holes. These electrons actually they absorb the oxygen. Actually the material absorb the oxygen, so the electrons facilitate the formation of superoxide radical from the oxygen. And similarly from the from the water or from the hydroxide ion, the holes will facilitate the formation of hydroxyl radicals. So these superoxide radicals and hydroxy radicals and holes, they will provide various degradation products like CO2 and H2O. So we have also studied the carbon footprint of our material, like how much carbon footprint our material is generating, because that is very much needed to prove the environmental sustainability of our process. So we have used 1 kg of catalyst. This is just an estimated carbon footprint for 1 kg catalyst preparation, and for the degradation of 100 kg of plastic weight, we have calculated it. So our process is generating 0.133 tons of CO2 in 28.1 days. So this is the conclusion of my work. So we have successfully prepared a bismuth oxychloride zirconium oxide nanocomposite and utilized it for the degradation of LDPE sample. So still we are studying the efficiency of this process for the degradation of microplastics. So that's all. Thank you very much.
Thank you for this presentation. So it's open for questions. If anybody
please.
Yeah.
Thank you for the nice talk. I have a question where you compare the degradation of 15 watt lamp with 90 watt lamps kinetics. So I was just wondering, your 90-watt curve looks sigmoidal the way everyone expects, like it increases and it goes to a saturation at some point. But maybe the other way around. But the other one shows like two distinct jumps. So that is probably a different mechanism. So could you please comment on that, why the mechanism differs? I mean, I can understand.
Actually, you can simply correlate with the intensity, because 90 watts will give you better intensity than 50 watts. More intensity means more degradation.
Yeah, the higher value is fine, but the nature of the curve was also...
Which curve?
Where you compare...
No, that is like weight loss experiment, that is. That is weight loss. You just put it under the light and you take the weight. So there is nothing like, there is no simulation, you just wait. You take the manual weight. Okay, it's not curve actually, it's not simulated, it's just weight. You just put it in the balance and weight it, how much it is coming.
Okay.
Yeah, please.
Very nice talk.
Yeah, thank you.
Just one comment. How do you confirm the homogeneity of your nanocomposite? That the your nanocomposite PiO, Cl and zirconium oxide is homogeneous over a spatial coordinate. How will you confirm it?
So it is uniformly dispersed or not?
Material composition is also uniformly dispersed.
Because we have make it a solution actually. We have stirred it and we make the film, that's it.
Okay.
So because if you stir it, we expect that it is uniformly dispersed, because we just added a fine powder, so it is already fine powder. So fine powder is dispersed and make it film actually.
Do you do any AFM or AFM studies or?
No, we have not done that.
Okay.
Thank you.
Any other questions? No. So in the TGA graph in the beginning,
Sir.
even after 600 degrees centigrade, there is a small slope change that I can see.
Yeah, sir, the bismuth oxide formation.
This is oxide here.
Bismuth
So
oxides.
oxide.
Yes, sir, bismuth oxides. Due to that only we have 27% and 12% weight loss actually. Thanks.
Okay. So no more questions, so we can thank the speaker
Thank you, sir.
again. Yeah, thank you.
Thank you, sir.